Is it an
Nobody. Say again?
Is it an FIR filter?
It is an FIR filter. Yes. It is an FIR filter that does what? What does it do?
Does it smooths out the output signal?
No, it smooths out the input signal. It smooths the input signal, and that's what the output is. You take a signal that has lots of peaks and valleys. You put it through a moving average filter, and then the output of that will be the smooth version. What kind of filter does it behave like?
A low pass filter.
A low pass filter. Low pass filter. All right. So let's just look at a three-term moving average filter. I'm going to increase this to 5-term in a minute. So 3 terms. So what's the difference equation then? What's the difference equation for such a thing?
Will a 3-term be Y event equal what it was 1/5?
Why you give me 1/5? You take an average. How do you take an average?
Oh, 1/3, sorry. That's X of N.
Yes.
Plus X of N minus 1.
Yes.
Plus X of N minus 2.
Okay. Good. So what's the impulse response of this?
You just can, wherever you see, let me see, that's 1/3. Open bracket delta of N. Plus delta of N minus 1. Plus delta of N minus 2.
What's the transfer function?
That's when we have defined the Z transform of H of N.
All right. Give it to me.
Oh. That will be, make sure I get it.
You said it. H of Z is the Z transform of H of N. So what's the problem? Take the Z transform of this.
Yeah, that'll just be 1 plus Z to the negative 1.
It's the third. I don't know why you're forgetting about the third. 1 plus
C to the negative 1 power plus C to the negative 2 power.
All right. And what's the frequency response? What's the frequency response? Just did this last class. Anybody, what's the frequency response?
Remember the frequency was response was H open bracket E to the power J omega. So,
All right. Sometimes we just abbreviate that to H of omega. Or what's that equal to?
and wherever we see Z, we put
Yeah.
E to the J.
E to what?
E to the J omega, right?
Yes. So this is E to the minus J omega. This here is E to the minus J 2 omega. And this is Spring's response. Response, and this is also equal to Y of omega over X of omega. And Y of omega is called the discrete time Fourier transform of X of n. And X of omega is called the discrete time Fourier transform, the Y of n, the X of n. Okay, this is something new today. We didn't do this last class. We did this last class. And Y of omega is simply Y of Z when Z equals E to the J omega. And X of omega is simply X of Z when Z equals E to J omega. And again, it's discrete time Fourier transform. Similar to taking the Fourier series of Y, except that it's not Fourier series, it's Fourier transform. It's Fourier transform. What's the magnitude response? What's the magnitude response?
Would not be the, I believe, in the numerator you would have the imaginary and the real at the top.
And
So
you
what
have
do
the conversion. You have to
excuse me?
when you have to convert the e to the j omega to cosine.
No. See, you all are telling me how to do it. I'm simply asking, what is it? I'm simply asking, what is the magnitude response? But you all are telling me how to do it. I'm going to ask that question after we establish what it is. What is the magnitude response? I'm going to the next page, the next slide. So take your snip. We have H omega is this. Call that the frequency response. And now I'm asking, what is the magnitude response?
That's
Okay.
the frequency response, right?
Say again?
Now I'm asking if it's the magnitude of the frequency response.
Exactly. When we ask for the magnitude response, we are actually asking for the magnitude of the frequency response. But quite often we don't say all that. We just say, what is the magnitude response? So that is the magnitude response. Magnitude response. Now tell me how to get it. Now tell me how to get it. We just did this last class, folks.
I know we have to convert the e to the power negative j omega to I think that'll be negative cosine.
No.
So it'll be cosine, probably cosine minus.
Then go ahead.
I said it's probably going to be in cosine minus j sine.
Yeah,
Put
man.
the root. Do we put the root first?
Why are you gonna put the root first? Why are you putting the root? Well, we'll get back to you about the root. We still need this. So we want the magnitude of that. But to find the magnitude of that, we need 1 plus cosine omega minus j sine omega. But Mr. Beauchamp wasn't pronouncing the omegas. What's the last term going to be?
Plus cosine omega.
No, look again.
2 omega.
2 omega.
All right. 2 omega minus j sine 2 omega.
Okay. And now this is an imaginary number. I mean, this is a complex number. What do we do?
Square roots.
No.
Okay.
We're not there yet.
Can I ask one thing?
Yes, that is a question. You want to ask another one?
Yeah, I want to ask another one. I understand that I only see one. I see two imaginary. That's the e to the power j omega and e to the power negative j 2 omega. Now,
That's not imaginary. That's complex.
oh,
See there? This is equal to this.
So the
Real number. Okay. Imaginary number.
yes, sir.
So I don't know why you're calling that imaginary. That's not imaginary. It's complex. And so is this. This is complex as also.
I didn't want to get confused. Thank you, Dr. Carter.
All right. Somebody was saying something. Somebody was saying
Actually,
somebody else.
do you group the real numbers together?
You have to. You have to agree that you don't do you do it. You have option to. No, you must. So it's one. Give me the real numbers.
1 plus cosine omega plus 2 cosine omega.
Yes.
And that's minus j sine omega. No, you're doing it like that, just sine omega plus sine. No, that's minus it. No, yeah, that's plus sine 2 omega.
Now, young man, we're ready for the square root sign. We can bring the 1/3 out. Now we're ready for the square root sign. Why? Because now we got the real part and the imaginary part.
Mm-hmm. So it'll be open bracket 1 plus cosine omega plus cosine 2 omega all squared
All squared, yes?
plus open bracket. That's what it is. Oh, you can put this whole thing, negative j.
No.
No, you don't put the j. Sorry, you put the sine omega plus the 2
Well,
sine.
technically, you're supposed to put the negative sine omega plus sine 2 omega, but it doesn't matter if you put that or not, because when you square it, it disappears. So that's the magnitude response.
You ain't got to go deeper than that, right?
No, not for this class. But you can. It's not that difficult. It's the phase response now. I'm going to the next slide. So as a reminder, A2 omega, 1/3, 1 plus e to the minus j omega plus e minus j2 omega. And discovered that was the third. 1 plus cosine omega plus cosine 2 omega minus j sine omega plus sine 2 omega. That's what we discovered. So the angle of h omega is the phase response. The phase response. Okay, what is that equal to?
Now, angle at the top minus angle at the bottom.
Yeah, what's the top? And what's the bottom?
The top would be the imaginary, and the bottom would be the real.
Me no top, me no bottom.
Complete nonsense,
Me
young
no
man.
top, no bottom. Me no star and a fraction. So that's how we
See,
do it.
Mr. Johnson, you memorize stuff without understanding what you're memorizing.
Yes, sir.
There is no numerator. There is only numerator. Yes, we could put all this over 1, but why bother? Because then the angle of the bottom would be 0. We don't need that. So what's the rule that's appropriate, Mr. Johnson? How do you find the phase of a complex number, Mr. Johnson? This is a complex number. Wow. Anybody? How do you find the phase?
Star and inverse, imaginary over the real.
Inverse tan of the imaginary. What's the imaginary?
I said I don't got it, but anyway,
Excuse me?
I know I didn't say that.
No, you were answering another question.
Yeah. Well, the imaginary, in this case, would be negative j open bracket sine omega.
No. The imaginary part has no j in it. The imaginary part is a coefficient of j. I don't know why we don't know this by now. When you find in magnitude and when you find in phase, there is no j. As a matter of fact, that's why you find in magnitude and phase, to get rid of the j. The imaginary part. Let's try again. What's the imaginary part? You see, you confuse an imaginary number. You confuse an imaginary number with an imaginary part. Those are two different things. I've been explaining this since 120. J5 is an imaginary number. The imaginary part is 5. The imaginary part is 5. The imaginary part is a coefficient of j. This is just terminology. That's all this is. When you say imaginary number to any learned individual, they know you mean j times some number. And the imaginary part is a coefficient of j. I don't know why we don't understand that by now. What's the imaginary part? What's the imaginary part of this complex number?
You mean Mr. Johnson?
Anybody?
Sine omega plus 2 sine omega.
No.
The negative sine omega
Yeah,
plus
negative.
2 sine.
Yes, it is. The imaginary part is negative sine omega plus sine 2 omega. What's the real part?
1 plus
Go ahead.
cosine omega plus cosine 2 omega.
Inverse sine of negative x is equal to what? Inverse sine of negative x equals what?
Was it
Negative. Negative inverse sine of x. So we can bring this negative sign out. So this is equal to inverse time sine omega plus sine 2 omega over 1 plus cosine omega plus cosine 2 omega.
Where you put the negative? I didn't see you put it.
I didn't put it. Thank you. I didn't put it, but it should have. So for all frequencies, for 0 to pi, the phase is negative. The phase of this moving average, three-term moving average, is negative. So all of this was reviewed, except for the new definition of discrete time Fourier transform, y of omega. That's the only new thing for today's lesson. Everything else was reviewed. Let's plot the magnitude response. And
The guy, you can put the page back, the last page you was on back. All right, thank you.
let's do it in octave. By let's, I mean you tell me. Okay, so I want to plot the magnitude response, and I want to plot the phase response. Two different graphs, just like we do it when we plot the magnitude response for low pass filter in analog, and the phase response of a low pass filter in analog. But we won't necessarily plot versus log frequency. We won't plot necessarily, although we could. With dB, we certainly can. Okay. So stop share. Let me see if that email was related to this course anyway. No, it's not. Okay, so we can continue. Somebody has a mic on. Please turn it off. Oh, okay. Should do. All right. Let's see this. ELR. ELR. Wow. I've forgotten that command because I haven't used it so long. Okay, it doesn't matter. I wanted to clear the screen, but apparently I've forgotten how to do that. Give me a second. Stop sharing for a second. Okay. All right. Yeah, let's see. Here we go. All right. I want to plot the mind response of what we just did. Come, tell me what to do.
Uh, do we have to do some kind of vectors?
Oh man, we're not even in the editor yet.
Oh, we have to create a file then.
How do we do that?
Mine to do a title, mine to page response dot m.
No. Edit.
Yeah.
I don't know why y'all don't remember this stuff. You got young minds. Actually, I know why you don't remember. You don't remember because you cram everything you do at the last minute. And then you got all kind of social media crap on your mind. And somebody right now looking at your phone to see what message you've got.
I didn't get my sleep last night. That's probably why a little slow to respond today.
Mr. Johnson, you are always this way. Edit. What file name you want to give this? How about three term? Three term MA filter .m. Okay. So we create that file. Then we now in the editor. Now what? Now what? let me remind you what we're trying to do. We're trying to plot the magnitude response. So what goes on the x-axis?
The real part.
The real part of what? I'm talking to everybody. I'm not just talking to Mr. Johnson. Wow. It's a magnitude response. Magnitude response means what?
Square root.
No, there you go again. There you go again. You're telling me how to calculate. You're not answering my question. What do we mean by magnitude response?
You mean the magnitude of the frequency response.
All right. And what is frequency response? What do we mean by frequency response?
That's h of omega.
So you're telling me the symbol, you're not telling me what it is. That is h of omega, but what is h of omega representing? What?
E to the power j omega.
No, that's not what h is representing. You're missing the whole point. You're missing the whole point of defining h of omega. What are you trying to accomplish when you define h of omega?
Trying to find the transfer function of the digital.
Mr. Johnson?
Yes, sir.
Give me a second, please. Okay. Mr. Johnson, what's the last thing you said?
I believe H omega is trying to find the transfer function of the digital frequency.
Ah, yes. At a given digital frequency, at a given digital frequency, what is the transfer function? That's exactly right. And the magnitude response is saying, I just want the magnitude part of that. I don't want the entire transfer function. I just want the magnitude of that. So when you find a magnitude response, you're finding the magnitude at a given frequency. So what's on the x-axis?
Are you sharing your screen?
I thought it was. What's on the x-axis? So what is on your x-axis? Wow. You're trying to plot a graph of the magnitude response. We just established magnitude response means magnitude of the transfer function at a given frequency. So what's on your x-axis?
One over three be on the x-axis.
1/3. I'm not even talking about any particular example. I'm not even talking. I am talking about the concept, just the concept of magnitude response. If you're going to plot a magnitude response curve, what's on your x-axis?
That's the frequency, and on the y-axis is the magnitude in dB.
Well, thank you very much. It don't have to be in dB. In analog, it's quite often in dB, but not even in analog is it always in dB. The magnitude is not always in dB. So our x-axis is digital frequency. Digital frequency. What's the minimum value of digital frequency?
It's 0 to pi, right?
0 to pi. So what's my first line here going to be? I'm trying to create a graph. What's my first line going to be? Just a second. Folks, how do I plot a graph?
You have the point.
I have to have points. Which points should I begin with?
X.
The x points. So how do I create my x points? What x points do I want?
If X
Yeah, would it be like x equals let's say 0 colon let's go to 10 semicolon something.
Well, we're not going to use x.
And no.
I'm going to use w. Why are you using n? And you're not in the time domain, Mr. Beauchamp. We're in the frequency domain. Transfer functions and frequency response, that's in the frequency domain. I'm just going to put comment here. Capital D, capital W is digital frequency. Because I don't want to be writing all omega. So W, capital W equals 0. 0 to pi, but we're going to space it 0.001 pi. So what did I just create? I created all my omega values. I just created all my omega values. And now what's the magnitude? What's the magnitude equal to?
Would we use y for that? Y equals.
Oh, why not magnitude?
Okay.
Magnitude equals what?
0 colon.
Oh, Lord. Folks, I am now dealing with the 3-term. I am now dealing with the 3-term moving average filter. What's the magnitude?
Would it no longer be negative 3 dB or?
Yo, man, we're trying to plot the magnitude. Why are you bringing up negative 3 dB? What is the magnitude, folks? What is the magnitude we're trying to plot?
Trying to find the magnitude of 1/3,
Yes?
open bracket, 1 plus e to the negative j omega.
Did we not develop a formula for the magnitude, Mr. Buchan?
Yeah, we developed the formula 1 plus cosine omega.
I'm gonna do in stages. So the real part we found out was 1 plus cosine of what? Capital W. Plus what? Cosine of 2 times W. That's the real part. And the imaginary part was negative sine of omega plus sine of 2 times omega. Right? Close bracket. Right? And then the magnitude was, a third, 1 divided by 3. 1 divided by 3 times the square root. The square root of what? The real squared. I have to do dot squared. Remember we talked about dot? Plus imaginary dot squared. Close bracket. And then we have the magnitude calculated. For every W value, for every omega value, we have the magnitude. That's what magnitude response means. How would you plot? Plot what? W on the x-axis and magnitude on the y-axis. I will pretty this up in a minute. Let's save this. And let's go here. I call the file.
Take out the drawdown.
Excuse me?
I was gonna remind you to take out the drawdown, but you remember.
Did I do lowercase somewhere? Yes, I did lowercase right here. That's a problem with Octave. It's case sensitive. PSpice is not case sensitive. See there? There's your magnitude response. There's your magnitude response on the x-axis, on the y-axis, the magnitude 0 to 1 on the y-axis, on the x-axis, the digital frequency. Now let's pretty it up. Now, I'm not just giving you this program. You would have looked at it, and you wouldn't even try to understand it. I hope you understand it better now. So we need an X label. X label. Digital frequency. Let me try something here. Let's see if that works. Yeah, you see there? You see there on the bottom? Digital frequency, the Greek symbol omega.
Yes, sir.
How did I create that omega? How did I create that omega?
You write it in, right?
Yeah, with the word.
Octave knows that code. And then a Y label. What's our Y label? Magnitude. And it's not in dB. The magnitude is not in dB, although we can make it in dB. Okay. And we want to grid on. And we want a title. And the title, what's the title going to be? Anybody, what's the title going to be?
Magnitude of the frequency response. So
No, we don't say magnitude of the frequency response. We just say magnitude response. First of all, is figure 1. Figure 1. Magnitude response. Magnitude response.
The third order.
Of 3 term. Not third order, 3 term. 3 term moving average. filter. Okay. And now let's close that. Let's save that. There's the magnitude. And my Zoom is hiding my title. Figure 1, magnitude response of three-term moving average filter. There it is. Okay. This is ugly in one respect. I don't like the fact that the graph ends before the curve ends before the graph in the area does. So I'm gonna try and change that if I remember how. I'm gonna do axis. That's gonna be a vector. I think 0, I, and then 0, 1. And I think that will do it. Let's see if it does. Yes, there it is. So I said what I want my the max scale and the minimum scale. I said what the minimum max scale should be, and what the minimum, the maximum Y scale should be. So now I have a nice little graph. And now how do I identify my cutoff frequency?
%70.
70%. Well, 0.707 really. So we go up here, and Mr. Johnson, I hope you could see it on your camera. We go up here where 0.707 is, and that's on the y-axis, 0.707, and I can't control that very well. Okay.
Look like
Oh, there, it looks like 0.98. The cutoff frequency, look at it. See, the Y value is 0.707. You see there in the left-hand corner?
Yeah, I see it now.
Yes, sir.
3.98.
Yeah.
The Y value is 0.707. And what's the X value? 0.98. So it looks like 0.98. And what is it theoretically? I gave this to you last class. What is it theoretically?
It was pi something.
You referring to the Y?
I'm referring to the cutoff frequency. What is the cutoff frequency of a moving average filter? If you folks would study, I wouldn't have to keep repeating myself.
You said 0.7.
No, 0.70 is not the cutoff frequency. .707 is the magnitude of the cutoff frequency. Please look at your notes from last class and tell me what the cutoff frequency should be.